state-of-the-art research when in a collaborative approaches with universities and other stakeholders. VITO provides our value by the applied research that connects fundamental research at very low TRL levels to different the stakeholders in companies, governments, and citizens, delivering them solutions that connect this very early stage research to fully developed technologies that are to solve real and concrete points of concrete problems in the society. The mission is to accelerate the transition to a sustainable world, and we believe that energy solutions are the key technologies to drive the green transition and support the development, the sustainable development, the sustainable mobility, and contribute to climate neutrality by 2050. And we also see that it stores sustainability services by providing the resiliency of the electricity systems that can bridge and access isolated communities, and also to solve the problems that we see here, for example, in South Africa, as disruption and outage of energy, provide grid service that support also the reduction of energy consumption for different stakeholders, particularly for large industries. Part of these solutions are also financial benefits that control the peak electricity demand, and of course to integrate the renewables into the grid towards mitigation of climate change impacts. Our research focuses on all the applications of energy solutions, particularly for batteries with large scale generation, also commercial and industrial storage, district storage, microgrids, energy communities, and of course mobility. What we see today, as most of you are aware of, we have seen a big growth in the availability of energy capacity over the years, more than multiplied by 5 in the last years, with a strong reduction of the cost. And we foresee for the future that this is a trend that is going to keep growing, particularly driven by the energy mobility. And in this trend, we observe also a shift from our current lithium-ion batteries to new chemistries, particularly for metal-sulfur chemistries, and transitioning for materials with more availability. The question that we pose today for environmental impacts that we have always to balance between the sustainability impacts, the reduction, for example, of the mineral extraction, and also for the reduction of carbon footprint and the reduction of the impacts of the production of these technologies. They have to be balanced all the time with the performance and expectations of the systems. And of course, there is a component of cost. And all environmental impacts and sustainability assessment must consider these 3 impacts, added to the challenge of social impacts that are particularly triggering us in the extraction of resources. The research today points this as the key aspects to address in terms of sustainability. The first is to increase the lifetime of the batteries, to innovate in the materials, to develop new recycling technologies, and also vehicle-to-grid technology, especially because we see that the future of batteries is going to be strongly linked to the development of electric mobility. And the main tools to assess the sustainability are the prospective life cycle assessment, in which you assess the impacts of today of a technology, considering its deployment in the future. And also, of course, life cycle sustainability assessment, that is a tool to integrate economic, social, and environmental impacts. Today, we are also very pressed by the regulatory framework. Particularly in Europe, we have seen this year the new battery directive that entered in force this year. And it stipulates for us a different set of requirements that will culminate in the battery passport in 2026. For this year, it's already mandatory to have a battery management system that is going to provide us information about the state of health of the battery and the state of discharge and all other relevant information that support us to assess the sustainability of the batteries in Europe. And with this information, we can provide perspectives for how they are going to behave, how they are going to can be improved or how they should be changed. Another thing that is particularly relevant for the environmental impacts is that from 2025, it's going to be mandatory to have the carbon footprint declaration for batteries. And when we have the battery passport, that is still a strong uncertainty for us. We still do not know, but it's going to establish all the chain of custody of the battery. It's going to inform us where the raw materials came from, how is the perspective of end of life, and you need to be prepared for this challenge in the future. This is very critical for research and also for assessing the sustainability impacts, because that supports us to understand how this battery is going to be in the market today and in the future, particularly for the chain of custody and responsibilities involved in its management. And for the future years, we see also important changes. Particularly, you're going to have different classes for the environmental performances of batteries. And in 2028, the maximum carbon footprint according to the different chemistries. Linked to that, we are going also to see requirements for minimum recycled content. And this recycled content starts to be enforced in 2028. And it's going to be extremely restrictive by 2031. And based on that, we believe that we have to work on the full supply chain of the batteries. And the full supply chain of batteries derives us with 4 main lines of research towards the sustainability, being the very first one, the raw material acquisition, and also the development of new active materials. And on that, we work on the sustainable recovery of raw materials, innovative materials also, new development of new chemistries, and also the development of new cathode and anode materials. For the use phase of the batteries, we work mostly in assessing the technical and performance aspects that derive us with different insights for regulatory aspects and for standardization. Finally, we have a line of research on battery recycling that manages all the end of life of these technologies, and particularly we address the innovative battery recycling technologies and advanced hydrometallurgy and direct recycling of batteries. And finally, covering all of this, we have the sustainability assessment of all the new developed technologies, also of the batteries already in the market, and all the new developments that we target as critical for the future of sustainable batteries. And on this, we perform life cycle sustainability assessments, prospective life cycle assessment, and techno-economic analysis that focus on the assessment of costs mostly and how they relate to the environmental impacts. I prepared a little bit of what we do in each of those lines. And in here, I show for one of our projects where we developed a new chemistry for a sodium battery. And in the new chemistry, developed new materials for the cathode materials and new materials for the electrolyte, always focusing on the recyclability. And based on it, we also provide assessments of the environmental impacts based on life cycle assessment. And in this the way of assessment can provide recommendations. For example, as in this project, we got to the conclusion that most of the impacts were derived by the battery model, and we can further dissecate these results to provide recommendations for each one of the components of the battery. And in this case, it was proven that our battery was performing better than an LFP battery, a benchmark one. And this is an integrated approach to assess how these new developments can be sustainable in the future. For the technical and performance aspects, we have strong expertise also in battery testing. Battery testings can be performed at the cell level and also at the module level. And they are critical because as we can identify the battery cycle, lifetime of the battery aging, the state of health, also the C rate of the battery, can provide recommendations for the development of new batteries for industrial partners. And this affects the life cycle of the battery and, of course, affects its sustainability because as long as we can monitor these parameters, we can provide recommendations to extend their lifetime and consequently reduce their environmental impacts. And on this, we have a full lab that it's for indoor testing of batteries at our campus. We perform a full range of tests. And these tests are also being reproduced here in South Africa in our partnership with CSIR. We have battery testbed project that you're going to visit today. And in this project, we are promoting the use of batteries and also providing technical knowledge to how to access these batteries according to different tests that can be used in the future for the assessment of their use and, of course, the environmental impacts when they are applied in large scale. We also believe in ecosystems of industrial companies that for energy storage. This is a picture of the Open Thor. It's a living lab, and in this living lab we have 2 different energy hubs. These energy hubs are equipped with battery systems that integrate residential, industrial, commercial, and also a stadium area. This can be considered an energy district. And we believe that this can provide the integration of the different energy technologies, not only for electricity, but also for heating and renewable generation and all different energy flows. Based on tests, on all this information that we gather from labs, we can provide further recommendations for the repurpose of batteries. And the purpose of batteries presents today a key aspect because we foresee a great number of batteries to be discarded by 2050. And it's relevant to understand how they are going to be repurposed for a second life and to extend their use. And like this, to avoid the production of new batteries in the future. We also work in different projects by providing new regulations and also support the development of new standards that will tell us how we can further develop methodologies that ensure that these repurposed batteries are going to be safe, reliable, and also how they can be integrated in a future market, especially because as of today, as for the economic pillar of sustainability, there is a big uncertainty of how we are going to have this new market of repurposed batteries. For the battery recycling technologies, today we have mostly 3 different routes for recycling. We have direct recycling, hydrometallurgic processes, and also pyrometallurgic processes. We work in direct recycling and also in recycling of batteries. And we are particularly focused in the direct recycling as it supports a faster and more straightforward path for the circularity of the batteries. In these processes, we have strong research in battery sorting as the key aspect of this chain of direct recycling. We also have recovery of cathode, anode, and metal separation. That's based on physical processes. We also have the recovery of the carbon black from the battery and also from the polyphenylidate fluoride by separation processes. And finally, we have relification and upcycling that supports the recovery of lithium and of the cathode materials. For the hydrometallurgic processes, we have been developing more chemically sustainable processes that minimize the use of chemicals in these processes, because I don't know if you're aware that we use several dissolution processes to recover the materials, and we are working in ways to develop better chemicals to provide this in a more sustainable way. Still on the end of life, today what we see is the characterization and sorting of batteries that is mostly done manually by operators, and this poses a strong challenge because these are, besides being highly dependent on their own knowledge, it's very dangerous for their health and also presents a safety issue because some of the batteries, they can have the potential of being explosive, of having been chemical materials leaking. And we have developed technologies that support the development, there's identification of each type of battery based on sensors, 3D laser triangulation technologies, and also in machine learning. And these machines that we have been developing, they characterize the materials using these different technologies, and also it trains algorithms to support the further assessment of these chemistries of these batteries, so we can have updates, for example, in terms of new chemistry entering the market, of new densities of cells, or all different characteristics that can change according to the manufacturer. Here we have a not not very special batteries, but this can be reproduced also for mobility batteries and for all kinds of energy batteries that we have. So this is the machine that we currently have. We are working now in the development of machines that not only characterize the materials, but also that automatize the process of sorting these materials to support different lines of recovery of these materials in an automated way that minimize the exposure of workers. And today, this new machine that is being used to characterize and sort is being currently under development and to be installed very soon in a facility in Belgium. Finally, for the assessment of the sustainability impacts, we work with life cycle assessment. That is also the topic of tomorrow for the workshop. Life cycle assessment assess the battery manufacturing as expected, but we also assess the full cycle of the battery. So we cover, for example, its use. In this example, it's from a project that was a battery from a vehicle, so a mobility battery. And then also, of course, the collection, dismantling, and recycling, but we also investigate the future pathways of this battery, since after first life, the battery typically after the use in a vehicle, it still has about 80% of its capacity, and a way to minimize its impacts is to consider different strategies for its life cycle, and this would require repurposing and also the consideration of their use in different applications. In this case, we considered it for a residential application, also for a utility case, and for an industry. Still on the life cycle assessment, we have a strong approach also for assessing the technologies on how they can evolve from today, as in the development stage, for in the future. So all the assessments that we conduct are linked to the research that is being provided, and it shows us how this technology is going to evolve for today in the future in terms of impacts, or for example, and if that's going to require more research, or if that's going to require, for example, different strategies during its implementation at industrial level. And the purpose of this is to assess the technologies to be future-proof, so you can provide sustainable solutions today that will remain sustainable, and also sustainable for research and for the market production, and to provide insights of the environmental impacts at the very early stages of development, so we can provide recommendations at the design stage of any of the new developments that we provide in any of the life cycle stages of the battery. And like this, we support to help the developers to reduce the time to market, because these recommendations support the assessment of which are the critical points, the hotspots that should be changed in the early stage of their development. So as takeaway messages for sustainability of batteries, we know that they are going to be key technologies for the energy transitions, and their presence in the market is going to grow. And we are going to see in the future not only more batteries, but more waste derived from the use. And we need technological innovation not only for the batteries per se, but also for the second use, the second life, for the repurposing, as well as for the treatment and end of life. And this technology should be also developed in a sustainable way, and we have to access them since the early stages of the development. So eco-design of not only of the batteries, but also the technology to be applied for the treatment and for the use. And tomorrow we have a workshop on the different methodologies that we use for that, especially for life cycle assessment. This is going to be developed in partnership with CSIR. We are going to explore a bit of the case studies that we have addressed in the past for the assessment of batteries. We are also going to present some of the aspects for what is required for LCA, and why we need for stakeholders to conduct this kind of study. And also, as CSIR is here, they are going to present us a bit of the existing requirements in South Africa for the further environmental assessment of batteries. So thank you very much.
time for questions. Any burning questions, or you can save them for tomorrow. This is just a teaser for the workshop, so perhaps if you don't have any burning questions, you know, save the questions for tomorrow. So I'll call on Tabo from CSIR to come and moderate the next session. Over to you. Tabo is the co-host from Fourm.
Good afternoon, stakeholders and partners. Once again, welcome to the 10th ESP meeting. My name is Thabo Hlalele. I lead the Energy Center at the CSIR. Okay, so perhaps while we're waiting for my slide to show up, I can briefly give an overview of where we are as a country and the importance of energy storage. I think from the Energy Center perspective in particular, we as the Energy Center have been involved in a number of research areas, particularly in the energy storage space. Most of you would know that South Africa has, ambitious targets around decarbonization of its economy to a low carbon economy. And to that end, over the last decade or so, we have essentially installed over 6 gigawatts of renewable energy sources. Now, renewable energy sources alone, they're significantly good and they're great in terms of the decarbonization agenda that we're trying to achieve. However, we know that for us to get to a point where we are able to accelerate the renewable energy penetration, we need a bit of stability in the grid. We need a bit of flexibility. And to that end, it is safe to say that we need alternative energy storage technologies that would come and support the integration of renewable energy sources. Now, I will briefly show you on a high level what we call this a secular energy storage metals economy in the context of the discussion that we'll be having today. In the context of South Africa, we have a very deep history in terms of extraction of minerals. And to that end, we've done a lot of manganese, we've done a lot of vanadium, which is going to be one of the discussions for today. We also have not so much in terms of the production of these energy storage. Be that as it may, CSIR over the years have done a massive amount of work in terms of the energy storage development. Now, you'll see that in the upstream, we've got the extraction and processing of these minerals, and we also have the important topic of recycling, which is going to be one of the other topics that we'll be discussing today with the team from the recycling team. Now, in the midstream part, from the CSIR perspective, we have done a number of work in the anode and cathode materials of the LMO, and I think most of you might also know of the Zebra type of batteries that we've also put to the market over the years. This also means that we know what we're talking about, and we've done it several times. But in the context of South Africa, are we doing enough of that? Perhaps that's going to be the discussion that we need to hear from our audience, from our panel, to actually elaborate more on that. We've also done a bit of battery packaging. I know that we are in the process of our first battery package, which is an LMO type of battery. Over and above that, that is coupled with the testing facilities that we have. And I think most of you will have the opportunity to visit our testing facility, which is the energy storage test bed, this afternoon. And coupled to that, we cannot just have the one part of testing the batteries without certifying those batteries. And this, in my view, is where SABS plays a critical part. And we'll also hear more about their testing facilities. And further down the value chain, we know that there's applications both in the mobility as well as the stationary application. So allow me to call the audience of the panelists today to be part of this discussion. I know that from Bushveld we will have Mikkel. Mikkel, can you please come join us? And then from SABS, Philip, can you please come join us? And finally, from EPR Waste, we'll have Malcolm. Malcolm, can you please come join us? Perhaps as a starting point, I would like to request Mikhail to give us an overview of the technology that they are doing from the mineral mining, extracting these minerals, as well as the applications related to your technology that you have in the context of the country.
Good afternoon, everyone. I lost my voice a few days ago. I promise I do not usually sound like this. If I lose my voice during the presentation, I have a colleague here, Mike, who will finish up. Thank you very much to the World Bank for continuing the ESB program, for starting it, actually, and continue it, and for the CSIR for hosting. This is now the second time the CSIR has hosted. Thank you very much for that. Just a little bit about me. I run Bushveld Energy. We're part of Bushveld Minerals, which produces 3.5% of the world's vanadium here in South Africa. I've got a facility in Mpumalanga and one in Northwest Province. We started the energy business. We've, together with the IDC, built one of the largest vanadium electrolyte facilities outside of China. We've also got a project development business. For those of you doing the site visits on Thursday, you'll actually see one of those projects that's been constructed already. I do wear a few other hats. I chair the South Africa Energy Storage Association, and I also chair the Energy Storage Committee of Vanatec, which is the Global Association of Vanadium Producers. So 3 things I'll cover today. I'll actually give an update on where vanadium energy storage is as a market. I'm actually not going to give you an intro into the technology too much. I did that a few years ago. I'm hoping people know what flow batteries are by now, but if you don't, then we can talk further. I'll give you an update on the supply chain. I think that's the critical thing for technologies to go from early commerciability to really kind of dominating the market or having a large portion of the market, and I'll share some thoughts on regulation and use cases. This is an old presentation. Okay. Do you have a new one? Because there was a couple of slides you wanted me to add on the tech. Okay. I've got it here as well. It's the only PowerPoint right on the drive. So the slide that I wanted to share, what is the difference between a flow battery? So I promised I wouldn't do an introduction, but I'll do a short one. The difference between a flow battery and, let's say, a lead-acid battery or a lithium battery that we're used to is, as the name suggests, it uses a liquid-based electrolyte. And so it's using basically chemical potential energy to store energy. And if we can go to slide 4, you'll see, yeah. And in a vanadium flow battery, there's only vanadium, sulfuric acid, and water. There are other flow batteries that use other combination of additives, but that's basically it. In one tank, you have a change in the oxidation state, and you have a reverse change in the other tank. Kind of your equivalent of a anode and cathode, but we call it analyte and catholyte. The batteries themselves can look very differently. Some can look like containers. Some can look like buildings. So the big batteries actually do look like that, and you can see inside some of the batteries there. So, like I said, there are other flow batteries, but basically vanadium is the dominant flow battery technology. 3 years ago, it was more than 90%, and that really hasn't changed. There are other chemistries like bromine, iron flow batteries, and then ferrochrome, but usually there's 1 or 2 companies supporting that technology. What we have in the vanadium space is about 50 companies that are either somewhere in R&D space, but a lot of them already have a commercial product and have been in the industry for quite a few years. About a quarter of those 50 companies are in China. As a result, there's a lot of activity in the supply chain, which is what I'll talk about. In China, there's dedicated technology policy specifically for the vanadium-based flow battery technology, but we're also seeing larger electrical equipment manufacturers that are not Chinese starting to use the tech. Siemens Gamesa is one, Voith is another. They do pumped hydro storage as well. At Vanitech, we at some point commissioned a study for what the growth rate for vanadium batteries is going to be globally. You can see it going from about 1 gigawatt hour in 2022 to over 20 gigawatt hours in 2031. So it's really, really fast growth, about 40%. It will also mean more than doubling of vanadium demand in that time. So now we're actually tracking to see whether or not these forecasts are accurate. The yellow part, which is called Asia Pacific, is just another term for China. Actually, the 2022 number was spot on. The non-Chinese use is actually quite a bit less, so it was only about 15%. So the forecast is fairly accurate because it's dependent upon China, but the rest of the world is not as aggressive on the tech as China is. Interestingly, though, we are starting to see a change on the global level. So this is showing what vanadium is being used for. And you can see that in 2018, 2021, those 4 years, about 2% of all vanadium went into batteries, flow batteries, and 92 went into steel. Other applications were other types of chemicals and high-strength alloys like with titanium. 2022, over 4% went into vanadium batteries. And then first half of this year, over 7% is going into vanadium batteries. And then steel has fallen to 85%. Part of that is steel demand is lower, but I think part of it is actually growth in vanadium demand for batteries. And if you look at this in China, which is the largest market for vanadium and one of the 2 largest markets for energy storage, about 10% of all vanadium is going into batteries. So yeah, China's dominating. We at Vanitech, with the support of the China Iron and Steel Research Institute, we're also tracking projects that are announced. This year so far, we've got about 4.5 gigawatt hours of vanadium batteries that have been announced in China. Look, they're pretty big. It's only 13 projects, and it's 4.5 gigawatt hours. In 2022, this number was 2 gigawatt hours for the whole year. Just caveat, these are announced projects. Doesn't mean all of them will get installed, but it also might mean that we don't know of all the projects as well. But it is not just a Chinese story. As you can see, vanadium batteries are being deployed globally in a lot of regions outside of China, in developed markets and in developing markets as well. I am not going to go through all of these examples, and even this is not an exhaustive list. The beauty is, if you're going to sites on Thursday, you're going to see a 4 megawatt hour flow battery that we've deployed at a project that we've developed. It's a mini grid tied to solar. I think there was a bit of an overview provided yesterday. So come out and see it. It's not too far from here. The other point I'll mention here is on the bottom. So the U.S. market to date has been very, very lithium focused. I mean, basically, the regulator there created a market for lithium batteries for ancillary services, and recently, a few years ago, expanded that to capacity. We're now actually seeing vanadium batteries starting to get a bit of traction in the U.S. Recently, a company called Invinity got awarded a tender for 84 megawatt hours of batteries. And we're seeing other companies like Sumitomo, H2, and CellCube deploying megawatt-size systems in the U.S. market as well. So, just like with battery deployments, China is also leading in the supply chain. These are vanadium electrolyte facilities that have been announced. You need electrolyte for the batteries. It's a key component, most expensive component. Not that many projects, 7 that we've saw. They really vary in size. 2 million liters. The largest one is 70 million liters. Just as an example, our facility that we've built with the IDC in East London is 8 million liters. So we're on the small side for China, but even within China, there's quite a bit of variability in the size. If we look at other components in battery assembly for vanadium batteries, there's a lot more than just electrolyte. So we've got about 30 projects that we have seen announced, and they vary in size quite a bit. Some are building a facility that does 100 megawatts. The largest one, there's a few gigafactories on this list, by the way. The largest one is 5 gigawatts. So usually manufacturing is done in gigawatts, and then the energy bit is done in gigawatt hours. So there could be some duplication here. So this includes companies that make components like the stacks. That's the second most expensive component after electrolyte. And then there's companies that are doing assembly. Obviously, it's going to be duplication in terms of the capacity. But this is a lot, and these are huge numbers in China. Now, just also, China's doing this for a lot of storage technologies, but this is as an example of really significant investment into the supply chain. Not just in R&D, this is manufacturing. There are examples in the supply chain activities outside of China as well. So while China is dominating, there are examples outside. In Australia, there's actually 2 electrolyte plants being installed this year, and there's some negotiations on local manufacturing. A metallurgical company called AMG has announced construction of an electrolyte plant in Germany. That should be done by the end of this year. They've also announced a construction of a project in Saudi Arabia. Actually, what AMG does is they take vanadium and other materials from spent catalysts. So they don't mine it, but they recover minerals that way. So they've got another project in Saudi together with Shell and a subsidiary of Aramco. And there's other examples there on manufacturing in Saudi as well. I've already mentioned our facility in East London. We've also expanded our own vanadium production capacity in Mekheleni in terms of how much vanadium we produce. And there, like I said, there's also examples in the U.S. where, because I think of the U.S. market, companies are looking for manufacturing opportunities. So what's driving this? And it's really policy, right? Why were batteries, kind of considered short duration 1 hour? Because that's what you could monetize. Why is now the benchmark 4 hours? Well, because you can only monetize 4 hours in the U.S. and everyone else has just followed suit. You don't get any credit for having a 5-hour battery in all the system operators in the U.S. and only one of them gives you credit up to 2 hours. So that's become a default, de facto kind of standard. That is changing. There's a recognition that systems require long duration storage, 4 hours, 6 hours, 8 hours, multi-day storage, probably even interseasonal storage. Flow batteries are cost effective for longer duration because the energy bit is decoupled from the power bit, so they become cheaper. In China, they have actually specific policies dedicated to the technology. That includes pilot facilities, which in China is 100 megawatts as a pilot, but they do it on a big scale there. But also the situation is that there's a lot of curtailment in certain provinces of China where there's a lot of renewable energy, especially wind. At the same time, there's a lot of issues with pollution. So while it's not necessarily a decarbonization agenda, it is I got to make life better for my citizens agenda. And wasting all this renewable energy is one of the issues. So vanadium batteries are used in some cases, to be coupled with new renewable generation. You may not even be able to get a permit without that for a new renewable plant, and in some cases for grid support. In Australia, they're just giving out grants for construction projects. In Canada, they're giving out grants for R&D. In the U.S. Recently designated vanadium as a critical material, and they're not supporting vanadium technology directly, but they're basically making tenders that exclude lithium and pumped hydro to have a technology diversification strategy, realizing that we have multiple minerals that we need, and we need a mix. Just like we need an energy mix, we need a storage mix. And so I think that's where the U.S. policy is going, and the expectation is that the Inflation Reduction Act will have more opportunities in that. The EU doesn't really have dedicated policies yet. Those are expected under their kind of Green Deal industrial plan. We're seeing like the EIB starting to finance some vanadium manufacturing. There's a lot of lobbying in Europe, though, for flow batteries. That's quite interesting. So I guess the question is, which policy levers can we use in developing countries? It's very sad that South Africa is not on here. The one thing we did do is we recognized vanadium as a critical material in 2019, but we don't have any other enabling policies for long duration or for vanadium batteries as other countries do. And I think part of it is to convince governments of the benefits of the policy action. So my final slide is just on some of the examples of the benefits of this action. So the reason why countries are doing this is because they realize that we need long duration storage to accelerate decarbonization, and I think also to support the power system, which is really an enabler for more renewables to be added faster. So in China, as I mentioned, it's actually done at the provincial level. The provinces where there's a lot of renewable energy generation are the ones that are actually seeing the implementation of vanadium supply chain manufacturing and vanadium battery deployment. And I think that use case of grid congestion and improving the amount of renewables is something that we can use here in South Africa as well. So I think that's a use case that's quite relevant. The other part that I wanted to mention is, we just saw a presentation on life cycle analysis, LCA. Texas A&M, one of multiple universities that have done research on the LCA of vanadium flow batteries, but they have concluded that combining wind in particular, but other renewable energy together with flow batteries, significant amount of carbon savings due to avoided curtailment. On top of that, a vanadium flow battery is less carbon intensive than a lithium battery for the same size, and that can be improved further because the electrolyte in the vanadium batteries can be reused. So while we have issues with what do we do with the lithium battery after it has kind of exhausted its 80% or 70% utilization, you've got to recycle it or redeploy it, eventually recycle it. The electrolyte in a flow battery can just be reused. So there, the chemistry, it's not about recycling, it's just about reusing it into another battery. So, and I think that, in the continent in general, where we have limited grids, there's a huge benefit for flow batteries for grid stabilization, and also to where there are no grids, to actually just decarbonize faster. Right now, we're seeing remote sites deploy just solar, and so they decarbonize 25% or 30% versus using diesel or heavy fuel oil. If you can add storage to that, you go to very, very cheaply to 70 to 90%. You still need some of that thermal energy to cover the seasonality of the solar, but that's a massive opportunity on the entire continent. And so I think combination of grid support and off-grid is the huge use case for Africa. Thank you. Hey, my voice survived.
Yeah, thanks, Mikael, for the excellent presentation. Perhaps before we go any further, most of you are aware that there's TIPS. I think you follow the TIPS numbers. The TIP numbers recently showed that South Africa imported over 4.4 billion rand of lithium ion, actually not billion rand, but USD of lithium ion batteries in the first half of this year. Now, while that is a good example of adoption of lithium ion for microgrid application or whatever the case may be, the challenge then becomes what are we doing in terms of testing and certifying those batteries? Now, the next speaker, Mr. Philip Khosana, will be giving us a bit of an overview around testing and certification, particularly in terms of the work that they're doing at the SABS. Mr. Philip?
Good afternoon, colleagues. I hope your DOD can go up to 95% after lunch. So is mine as well. Thanks, Thabo, for the introduction. My name is Philip, and I'm from the SABS Standards. And I will take you through what the SABS is doing around renewable energy and energy storage. Next slide, please. I'm not seeing anything. Oh, yes. But it's not appearing. We can use this if there are challenges. All right. Yeah, I have it on the computer, but I don't have a stick. Okay. Sorry about that, colleagues. Just a background on how we go around developing the South African national standards. In as much as other countries, they also have their own national standards. The main reason why we have the SABS is because of an enactment of the Standards Act of 2008, and which mandates the SABS to develop and to promote and to maintain the South African national standards. We do so through the collaboration of many technical expertise in many areas. But we don't only develop standards, as Thabo has indicated. We are also privileged to have the laboratories to test certain products. We may not be able to test all the products for the standards that we develop. And we also have certifications for some of the products as per the customer requirements. Colleagues, we are not only looking at the nationally developed standards, but we also collaborate with international committees like your IEC, which is, just to elaborate for those who may confuse the IEC with Electoral Commission. This is International Electrotechnical Commission, and we also have ISO, which is International Standards Organization, and also the ITU, which is not here, but there is the International Telecommunication Unions. So how do we go about participating at the international level on the IEC and the ISO? In most cases, you will find colleagues giving us queries about the IEC documents. Colleagues, when you see the IEC documents, just know that South Africa is a member of the IEC. I have Rinesh there at the back. Rinesh is also participating in energy storage on the IEC committee. I have other colleagues who are also participating in batteries. I have Hiten there, is also a member of the IEC. So we are not only developing South African national standard, but we make sure that the IEC, the documents that the IEC that are going to publish, we also need to have an influence on those standards. And one of the biggest, I might say, it might be a trend, is that most of us, we only think about standards when there is an incident. And somebody will ask, but why didn't, for example, our use building, you did not build according to the standard when there are problems? For me, I don't need a regulation for me to perform a certain action in terms of a standard. Apply the standard first, and while you are applying the standard, just know that you were involved in part of developing the standard. If you are not sure, get your other colleagues to be involved in our committees so that your inputs in your field of work can be taken into account. I'm going to mention two committees. We have several committees, but I will mention two committees, which is energy storage. This is the SABS Technical Committee, and we also have a Technical Committee TC69. TC69, we have power electronics and alternative energy conversion. Mostly we have the renewables. I'll come to the next slide. And on TC63, mainly we have batteries, fuel cell, and other committees that we liaise with. At the center, you have TC63, And we also have 4 of the IEC committees. The IEC TC21, it also have a subcommittee, which is SC21A. These are battery committees, which mainly focuses on battery energy storage. And we have TC120, which is electrical energy storage systems. And we also have, my mistake, I repeated TC21, apologies for that. We have TC82, which is photovoltaic energy systems. And the other one that I will partially mention as well, it used to be called wind turbines, but it's wind energy generation systems. As I said, we have different expertise from local committees who also participate in this particular committees. Before I move ahead, I'm going to give you the scope of what these other committees are doing, and you may look into those committees if you want to be involved in those particular committees. But for the local committee of SABS TC63, we have published for up to this year, we have published up to 63 national standards, which includes the adoption of the IEC standards. And when we adopt in accordance to what the industry needs. We don't just publish for the sake of taking everything from the IEC. But if you need a particular document for South African national standards, then we adopt that particular product from the IEC. The scope of TC21, these are secondary batteries. If you look at it, you also have safety rules for installation, operation, and maintenance and disposal of batteries, meaning the recycling that we have been talking about is also being taken care of in the IEC TC21. I will mention some few as we go along. I will mention some few of the standards that may be applicable. It has not yet been published. If you are interested, you may also form part of the development of that particular standard based on recycling of secondary batteries. I hope when we go to the recycling plant, we'll be able to see what is being displayed there in terms of recycling of batteries. And we also have TC120, which is energy storage system, electrical energy storage system. It caters for all the renewables. It caters for your batteries. It also caters for some of the hydrogen fuel cells, but partially so because we also have a committee on fuel cells, which is the next IEC TC 105, which is the scope for fuel cells. Colleagues, if I'm maybe speaking too fast, you can stop me. Maybe just to go back just a little bit on what the TC21, we have the working groups. In TC21, it's divided into working groups. And one of the interesting working groups from my side, it's secondary lithium cells and batteries for industrial application. As it has been mentioned by Thabo here that we are exporting a lot of lithium, and I must also concur with him that in the past 2 or 3 years, every month there will be an inquiry from an importer asking about the regulations that are required for an importer to bring in these products into South Africa. I must also caution you that I think testing, we'll talk about it at a later stage, I think testing is very important because we do have those so-called golden samples where somebody just put a label that says this product conforms to SANS whatever, or it is approved by the SABS. So for you to be assured of that, you can take your product to whatever test facilities including ours, to test your particular products to make sure that you are using safe products. In TC 21A, we have a couple of working groups, but I'll only mention only one because of the interest in lithium batteries. We also have working groups in the other TC 21 and the other TC. If you allow me, I can just mention in passing. In TC, one of the biggest technical committees of the IEC is TC 82, which is solar photovoltaic system. Colleagues, you cannot just use photovoltaics without energy storage. That has changed over the years. While the efficiency of modules are improving, but we also need the improvement of energy storage systems like our batteries. So in TC 82 of the IEC, we have over 100 participants in one working group, which says to us that there is more interest in this particular working group. And I would encourage fellow South Africans who are expert in those fields to also take part in those different working groups. It doesn't take much of your time. One document, we can give you 3 months to review the document of 15 pages. You can read 1 page per day, so it will be enough. Colleagues, here we have fuel cells and battery standards. The first one, I hope you'll be able to see. I've only highlighted a few in terms of the demand that we are seeing from our colleagues in the industry. The first one is SAN 62620. This is the specification for lithium-ion batteries. CSIR, I think today we are visiting the lab where we'll be able to see some of the tests that are being performed on the SAN 62620. Maybe I should have mentioned that it's also an adoption from the IEC. As we speak currently, this particular document, it was amended recently, but after the amendment, because of its demand and the safety aspect, now it is now being revised. So you are also welcome to make your comments on this particular document. The 62620, it goes along with 62619. Both of them are industrial applications. And the 62485-2 is also for safety of batteries. This particular one is stationary batteries and the installation thereof. On the part of the fuel cells, my colleague here was mentioning the safety of hydrogen. Hydrogen, I guess, is just like computers. You don't use it to harm people. You use it for your own advantage. So there are experts out there who are working on the safety aspects of every component that we are working on. So if you are interested mainly on the safety of hydrogen, please, you are welcome. The gentleman behind you is the one who's going to register you on the IEC so that you become a member of the big family. I must also say, without promoting only the SABS, I must say, colleagues, to participate internationally is of big value because in some other instances, there might be mistakes or the South African market might not be catered for in the document. Only when you want to apply the standard, you only find that it is not really applicable for your needs because the South African needs were not catered for. So your participation at this level is paramount for us. The last one we have not yet adopted the standard, which is for grid integration of energy storage systems, electrochemical based systems, and number 5 there is photovoltaic off-grid applications. So if you look, there is an harmony between the photovoltaics. Unfortunately, I didn't include the wind energy generation systems, but there is an harmony between the PVs and energy storage. Colleagues, if I may ask, is it possible to have energy storage which is working with batteries without the inverters? I don't know. I'm just asking. Is it possible? Is it possible without an inverter? Yes. You have a battery and then you have a PV, no inverter. Somebody says yes. Is there a different opinion?
If you're on a DC system, it's possible. Theoretically possible.
Thank you for the conversation. Thank you for the conversation. So it shows, colleagues, that there will be applications where you need an harmony between the systems, including the PVs. So the PVs are not excluded in this energy storage systems. I'm going backwards. The PVs are not excluded in the energy storage systems. If you look at TC69, as I said, is power electronics, where we are going to talk about inverters. So TC88 is for wind energy generation systems, and TC82 is for photovoltaic systems, and the System Committee on LVDC. I don't know if you are aware, colleagues, that these days you can have a refrigerator that is off-grid, or you can even have your washing machine from macro, which is a DC appliance without any conversion. In any case, the refrigerator, these are DC, but they are using a conversion system. But now you can have a direct PV, I mean not PV, DC appliance. So some of the new technologies, we are trying to move there, and even though they are not cheaper, as you know, technology starts being expensive and then later on becomes cheaper. So these are the committees that we are collaborating with. I mainly participate on TC82, and yeah, you can interact with me regarding the inverters and the challenges of the inverters. This is the scope for TC82. It can also be found on the IEC website. And this particular TC82 is only for this particular suite of standards, which is for rural electrification. The IEC TS 62257. So if you look at the mapping there, in terms of the development of standard, it covers all these areas that have been shown on the map here. You can have an off-grid system. You can also have grid-tied applications, and you also have those plug and play. But colleagues, I must say, in terms of regulations, certification, and testing, when we started having some serious load shedding, I don't know how many lights, rechargeable lights, that I have bought and discarded. I think somebody can advise me. I think 2 or 3 weeks ago, there was a drive from Macro where they were collecting all this used electronics, and then you were being rewarded for that. Apparently, there was a long queue. I missed it because I could have made money because of the products that really do not last for that long. And I'm going to borrow from one of my colleagues who was presenting yesterday, surname Mr. Nyati. I don't know if he's here. He spoke about the graveyard for the PVs. We buy these products. They don't last for long. We don't test them because we need them at the moment, and we just take them off the shelf, and then after 2 months or even after 3 months, those products are dead. So I must say, for now, I've been assigned one of the projects in IEC where we will be investigating by visual inspection, where we'll be investigating the modules that are damaged and how to spot those particular modules before you can even take them for testing. I was giving one of my colleagues example that Philip might be an expert in installation of PV, expert. Then when I transport these PV modules to your house, I don't even know how they should be transported, but when I load them or when I put them on the roof, only to find that some of the modules have already been damaged from your shop to your house, and they are not performing efficiently. So we will be publishing that particular document as to how to spot those errors or mistakes that could be on the modules. Without much waste of time, colleagues, on TC82, as I indicated that we have LVDC as well. This is something that is new or that is developing rapidly, and the products they are already on the market. And the reason, of course, I don't want to go into too much technicality. We look at the standards that we are publishing and their purposes and the test that we can be doing. So we will be covering the standards in terms of the purpose and in terms of the test. We'll also be looking into grid integration. As you would know that the grid code is the guideline, but we also have products from the IEC which also talks about the grid integration. And we'll also mainly talking about safety, which is key for the layman and for the installers. That is paramount for us when we adopt this particular standards or when we develop this particular standards. The last one, which is almost the same as the previous slide, we're looking at the energy storage system application. We define the performance criteria, the testing procedures, and we also evaluate performance. It is no use to have this fancy, let's say, example, a battery, which is going to only last for, I'll speak from experience, which is only going to last for 1 year. I'm speaking from experience. I will not mention which one it is. Thabo, you spoke about certification and testing. We work with partners in terms of the NERSA, that is the national regulator. They will specify the grid codes and what is required. But in terms of product regulations, we have the national compulsory for compulsory specification, which is the NRCS. As we are speaking, we are awaiting the DTIC to sign the regulation on lithium-ion batteries. I've seen my colleagues was presenting many countries like European Union. They also have a regulation on lithium-ion batteries. Colleagues, I might speak for more than what is required. I think this is from my side. Thank you for your attention.
Thank you once again, Phil, for giving us a framework from which the energy storage or lithium-ion batteries as well as renewable energy or PV are currently being tested. With that said, I think it's also good now to understand, throughout the entire life cycle, the recycling process. And we are glad to have Malcolm here to give us an overview of what is it that they're doing from the e-waste point of view and how do we circle back, because on the one end we making sure that we are applying these energy storage, but once they reach the end of life, what do we do? So Malcolm, please, come share.
Thank you, Thabo. Good afternoon, ladies and gentlemen. I was going to ask you to all quickly stand and just stretch because, that graveyard shift. So, anyway, good. My name is Malcolm Whitehouse. I'm the Operations Executive for IWASA. And IWASA used to be the E-Waste Association of South Africa. It's now called the EPR Waste Association of South Africa under the extended producer regulations for different waste categories. So I'm just going to give a brief overview of who we are. We were established in 2008 to manage the establishment of a sustainable, environmentally sound waste management system for South Africa. We're a level 2 BEE NPC or PRO and PRO as well. And since our inception, we've been working with manufacturers, vendors, and distributors of EEE which is electronics and electrical goods, paper and packaging, lighting, and now recently with portable batteries, as that came into the EPR legislation in March this year, as well as also with waste handlers who manage the waste in order to manage the waste effectively. This entails education and training, enterprise development, research and development, beneficiation of waste, job creation, social compacts, and then managing the EPR schemes on behalf of the producers. We registered with the Department of Forestry, Fisheries and Environment under the DFFE Section 18 Extended Producer Responsibility Registry in the 4 categories of EEE, packaging, lighting, and portable batteries. So just a couple of challenges that we've picked up as an EPR. I'm going to say this because we were highly specialized in the e-waste side of things, more on your ICT equipment. But as things grew, I actually was just reminded, Philip, when I was in the recycling sector back in 2012, when I think it was 2012, they started building the solar farm. I was approached by the people that were importing the panels, and they wanted to deliver 40 tons a week of panels that had been written off in transit for us to recycle, and we just didn't have the technology back in those days. So it's a very real problem, and it's been long-standing. Just a quick one on EPR. What we do is we have producer members that pay a levy that has been authorized by the minister through a concurrence letter. They pay that levy into the PRO, and then with that levy we do a lot of different things, and one of them is to do research and development to find technology for the more problematic waste fractions. Currently, we have found that the quite expensive solutions for lithium-ion battery recycling, and most recyclers that have the desire and the appetite to do so send their batteries to the EU, to places like Umicore in Belgium for final recycling or treatment. I know we did that when I was back in the industry and myself in those days, and that was very costly, and it's very complex and complicated because you can imagine the dangerous goods transport side of things, the shipping costs, the pollution insurance requirements, etc. It also invokes the Basel Convention, prior informed protocol, or prior informed consent for transport of hazardous substances transboundary, which makes life even more exciting. Some of the issues we had in the past were applications for licenses taking up to, or permits up to 16 to 19 months to move a shipment. So it becomes quite expensive. Also cost negative because you had to pay for the recycling. There was no rebate for the recyclers. And being in the recycling industry, pretty much the big problem is it's a high cost, high volume, and low margin type of business. And then current recycling facilities are locally are charging gate fees higher than the EPR levies. And that's a discussion that my colleague and I are going to have next week, a bit more about sitting over there, Pravashan. So in terms of the current assessment that we have of the situation in South Africa, there are only 2 properly compliant recycling facilities for the recycling of LIBs in South Africa, which are charging the gate fees, understandably so because of the cost of investment, the high capital costs, and the building up of the infrastructure. It doesn't come cheap. There are, however, a number of other smaller players that are dabbling in finding solutions for LIB recycling in South Africa. There's a lack of reliable data on the quantities of the waste lithium-ion battery materials that are potentially available for recycling, and also the origins and the flows, the intermediate and final markets for the lithium-ion battery fractions. And such information obviously is critical in informing the decisions of technology process selection, as well as determining the economics of the selection process. In terms of local collaboration in finding local recycling solutions between IWASA and other stakeholders, we have engaged and we are continuing to engage with various stakeholders under our EPR mandate to do the research and development and find and establish technology solutions for local recycling of lithium-ion batteries. And remember, in our industry, a lot of the percentage of recycling comes from ICT equipment and mobile phones and laptops, which are currently the biggest sort of contributors to lithium-ion batteries in this country. Modular and less capital-intensive solutions are being developed locally to have smaller facilities established in main centers. Because of the challenge around transporting batteries under the Dangerous Goods Act, because you have to handle the stuff properly, and there's a host of other issues. The devices have to be discharged, and they have to be managed in a safe way. And one of my other colleagues from the same industry refers to a thermal event and not a fire. He says it's something next level. And I fly a radio-controlled aircraft, and I've seen a small little lithium battery explode and burn, and I tell you what, it was quite amazing. So this will equate to lower logistics costs and lower critical mass volumes required to run the technology, because that is always a challenge. It's more economically viable in the long term and more economically sustainable. And then you have the ease of transporting various fractions to bigger centralized facilities for the final treatment once it's been aggregated. So currently we're busy with a partnership with EMPA in Switzerland, the Material Science and Technology Foundation, Stellenbosch University, the UJ Peets, or University of Johannesburg Processed Energy and Environmental Training Station, the Course of Business, TCB, the African Reclaimers Organization, because we have to integrate. This is one of the big challenges that we have. We have to integrate the waste reclaimers, because they go around with the trolleys collecting all sorts of waste materials. So they need to be trained on how to deal with these fractions safely, and then also with eco work in India and Switzerland in developing a solution. So there's funding that's been put aside. We're looking at different technologies. There'll be the research partner from Switzerland, the research partner country, the development actor, which would probably be TCB, and Arrow, the Reclaimers Association, in conjunction with IWASA, as well as the other players that are currently within the market at the moment, so that we can find something that's going to work for this country's solution. A lot of the European and global technology, we can learn from all of that, because we need to learn from lessons learned before, but we then need to take that and we need to modify it to suit the local conditions, because there's different demographics, there's different culture, there's a different approach to everything and the way things work in South Africa. And then we'll have a subcontractor project partner from the global north and a development partner as well. Just in terms of a pre-proposal, I know it looks like a very, very complex diagram, but service package 1 would be, it will be multi-stakeholder engagement connecting the network in the global south, data collection and analysis to inform the ecosystem and the transition systems, design and piloting of the end-of-life lithium battery management, managing the hazardous fractions and the recycling side of things, modeling the end-of-life lithium batteries from a material, environmental, and economic perspective, and then transfer, knowledge, dissemination, and outreach. And that will all go in terms of the use of the batteries, stockpiling, collection, repair, reuse, refurbishment, recovery, disassembly, discharge, both the formal and informal sector integration, and then also from a manufacturing perspective. We're currently working with these two organizations, Kwenga and Uyilo. I think Kwenga, you're going to do a site visit either today or tomorrow. Thursday, yes, to go and see what they're doing there. So in terms of the way we're looking at it, from an IWASA perspective, we're looking at the protocol development and implementation, service agreements and facilities, and that will deal with, basically, if you look over there, your collecting, your domestic side, your commercial, and then your decentralized facilities and OEMs, so that we can work all of that out together. Then your neutralization and pretreatment, and then Quenga themselves will look at the process development and pilot and techno-economics, where they're doing the extraction and purification and centralized in a centralized facility, and then battery chemicals and materials with those metals that are coming out of it through ULO with their facilities and skills, and then also their techno-economics. So we're busy building that consortium and looking at establishing a workable solution for the smaller lithium-ion batteries. As we go along, part of the EPR mandate we will have to then look at growing in terms of the electric vehicle battery requirements. We will be engaging more and more with the CSIR, with the SABS, etc., so that we can, I think something that we found with the EPR regulations, the uptake from the producer side has been very difficult in terms of people are having to pay a levy to put their product on market, and they want to know what we're doing with the money. And they're saying, well, we don't want to do that because that puts us at a competitive disadvantage. But the government has adopted the attitude from the producer pays principle through the department, and the EPR regulations were developed so that we could take those fees and those levies and develop the sector, because we've been caught, in my opinion, off guard from an electronic waste management perspective. The solar panels and the lithium batteries have grown rapidly. Thabo is referring to, and I think Philip, you're referring to the load shedding crisis. I think the amount of batteries and stuff that have been placed on market, that's all going to come into the waste stream. Then the other thing is solar panels were put into play 25 years ago, and people are replacing those panels, and what do they do with them? Where do they go with them? So we need to find suitable solutions for that. Then just some of the drivers for the recycling of lithium-ion batteries: environmental considerations, the need for critical raw materials, reducing the reliance on primary mining activities. Forgive me, Miguel, but you've got lots of other exciting technologies that you're bringing to the party with your operations, compliance with regulations, and then generation of local economic activities. The technology landscape and business case for the recycling of lithium-ion batteries in South Africa: some of the key findings of the study completed by Mintech was the low LIB waste collection volumes. They've estimated that South Africa has collected 6 to 10 tons of lithium-ion batteries or battery waste from waste electronic and electrical equipment, or recycling activities, in 2019. However, DFFE's banning of landfilling of lithium-ion batteries in August 2021, sorry, that's supposed to be 2021, not 2012, can change this, as was the case with the lighting equipment ban in August of 2016. Then laptop and mobile phones are the major source of waste streams for lithium-ion battery waste recovery, and as they are a major source, there's no evidence of LIB waste recovered from industrial equipment at this point in time, like forklifts and scooters and electric vehicles, which will then eventually join the recycling value chain. The storage and transportation of lithium-ion batteries are major challenges for recyclers, because they need to, first of all, the storage of lithium-ion batteries waste to accumulate sufficient volumes on site, and transportation of the material to the market are major operational challenges for the recycling company. And I mentioned it a bit earlier on. I worked for a company, and we collected cell phone batteries back in the day when they could still be removed from the device, and it took 4 years for us to fill a 6-meter container to collect enough product. So you had to store that for 4 years, plus you had the risk of the fire and all the other challenges that came with it. And then it was to find the suitable shipping company that had the dangerous good qualifications, shipping it, getting it onto a shipping line, very, very expensive environmental pollution insurance. I think back in those days, in the EPR, any electronic device placed on market has to go through a whole lithium, I beg your pardon, a life cycle assessment. And I know the CSIR developed a whole guideline and toolkit that we use to actually determine that with our producer members. just some of the main types of lithium-ion battery cell chemistry: the lithium cobalt oxide, the lithium manganese oxide. The first one is from mobile phones and laptops. The LMO is from hybrid EV cell phones and laptops. The lithium nickel manganese cobalt oxide, EV industrial applications, power tools. A lot of wherever you go these days, you can buy power tools. It's so cool and so convenient because I'm a carpenter as a sideline at home. So it's nice to have all these power tools, but they all have batteries that are going to have to be recycled at the end of the life. And again, that issue about buying the stuff cheaply, you buy it once and then suddenly in 6 months or a year, you've got to throw it away, or it's no longer useful. You've got to spend money to get the right stuff. The lithium iron phosphate, renewable energy storage, e-bikes, electric vehicles, etc. We just had one of the importers of e-bikes join us, and we're engaging with them to find solutions for their end of life. So they're preempting it as well, which is a good thing. Lithium, nickel, cobalt, aluminium oxide, EV renewable energy storage, and lithium titanate, EV and electronic devices. Sorry, I'm not an expert on these fancy metals and that, so forgive me if I get the names wrong. And then we just say things are easier when you work together through partnerships and service level agreements between ourselves, our producers, the recyclers, academia, civil society, DFFE, and NGOs and NFPs. And I thank you very much for your time.
Thank you, Malcolm. Very informative and insightful presentation around our role as far as recycling is concerned. I will now open the floor for questions from the audience in terms of points that I would like to get further clarification on. Are there any questions from the audience? Yeah, perhaps. Where's the mic?
Okay. Malcolm, this is a question for you. I just don't want to stand over you right now. The question is about the PROs, the Producer Responsibility Organizations. Can you just give us clarification on how, is it different PROs? Are they working together? Because it seems, there's different sort of paths that people are taking. Is there some sort of future standardization per se in approaching what the EPR sort of is supposed to be in a sense?
Thank you, and I did see that your name was Tabu. That's a good question, Tabu. At this point in time, there are different PROs. There's in the plastics industry, there's quite a few, the metals, and as we grow, I believe that they may reduce and whittle to more sort of select ones, because just to run the PRO and what we have to do, I think it speaks for itself. I've had a couple of producers saying, "Oh, well, we'll just do it on our own." I said, "Well, great, go for it, Your core business is bringing goods in and selling them. That, let us manage that for you on your behalf." And that's why, as UASA, we chose to register in the 4 categories so that it would almost be a one-stop shop. But in terms of the PROs going forward, it's a matter of really understanding the ethos and the spirit of EPR and what it's designed to do. It's not designed to wield the big stick. For instance, electronic waste is the fastest growing waste stream globally, with 54 million tons being placed on market every year in the world, and around 25% being recycled. In this country, 415,000 tons a year, 7 to 12% is recycled. And the value of the secondary resource materials is just astronomical. You're sitting at about 80% plus of all solid waste that goes into landfill these days that has value of some sort or another. So, if we just focus on fixing the problem and trying to help with the design for recycling, etc., going forward, then I believe it will eventually sort itself out into. Okay.
Thanks, Mike. I'm aware that we only have a minute, so we can possibly just take one question before the break. There's someone already behind you. Perhaps just yeah.
My question is for Kyle and Philip. Kyle, when you presented, you showed a trajectory of for the growth of vanadium batteries. And the growth I'm not sure if that was Africa or South Africa specifically, was quite small. So I was wondering if you can explain why that is. And for Philip, if you can just elaborate on the work groups that are currently working on other battery technologies other than the lithium ion. And for Philip again, I know you guys have a lot of standards, but at what point do you intend on making those standards law, as in have them in the OSH Act, so that there is legal liability to actually keeping them?
Okay, so let me address the forecast one. It's because the forecasting agencies, I think, just ignore Africa. To be honest, that's like an understated story right now is South Africa probably has a top 5, possibly a top 3 residential battery market in the world. There's very little on that. S&P had a bullet point that it was the fastest growing in the world, but if you just look at how much it is and you compare it to, like, say, the German market, which was actually the largest residential market up until last year, we are at that same level where Germany was last year. So that's the reason, and I don't think anyone forecasted that South Africa would be there, even though we knew load shedding was coming, and it was already the case. So I think that's why it's under forecast. The same is happening. No one's tracking globally the fact that we have huge utility procurement going on, both by ESCOM, which was initially funded by the World Bank, and by the IPP office. There's another 1,200 megawatts, right, which is 4-hour duration, 5 gigawatt hours that's going to come out after this initial round is announced for the private sector. So I think they're just not, at the moment, factoring it in, but they will.
I didn't get your name. Maybe I would prefer to call you by the name. Nkele. Nkele, I'll start with the last one in terms of making standards law. The Act of Standards Act does not actually dictate that the standards are compulsory. Like I indicated that we have regulators. One of them is the NRCS, which you, Ngele, yourself, you can make a standard a law by making a proposal to the NRCS that we want to regulate this particular standard, mainly where safety is concerned. So you can make that proposal to the NRCS and also the Department of, is it Labor and, yeah, also to the Department of Labor. Mainly the Department of Labor, they will regulate installations on premises. But for the products, you can approach the NRCS and make a proposal as an individual, never mind the organization. The other part on working groups, which particular, are you referring to the batteries or the committees that we're talking about? It may not only be lithium. On subcommittee 1, we have about 7 working groups. Number 7 is aircraft, just for an example. But maybe for simplicity, if you go to iec.ch, then when you go to iec.ch, you look at the list of technical committees.
they will give you the names of those technical committees. Then you can see on the structure which working groups might be of interest to you. So the ones that I have here, it will be secondary alkaline batteries for industrial application. That's working group number 1. And they will all be secondary. So I'll just skip secondary. And the batteries for portable applications, batteries for secondary batteries, cells, and batteries for portable application. It seems to be repeating itself. The other one is environmental issues related to secondary cells, batteries containing alkaline or non-acidic electrolytes. So those are the working groups that we have on the subcommittee 7. We have other working groups. Some of them we have what we call joint working groups. The joint working groups, it's a collaboration between, let's say, the battery standards and also the PV standards. Because as I said, these committees, they need to work in a harmony where you have a system. So you'll have many committees. So maybe after this, if you want to interact with me, I can just share with you the number of committees that we have there. Is that okay?
Thanks, Phil, for the response. With that, colleagues, I'd like to say thank you, and we may continue with the break.